Hey guys, and welcome to the last lecture for organic chemistry this semester. We've been talking a lot about spectroscopy, and we're going to introduce our last spectroscopy here, which is mass spectrometry. Mass spectrometry is an analytical technique that measures the mass to charge ratio of ions. This is particularly helpful in determining molecular mass, and it's become more helpful in recent years in protein sequencing. A mass spectrometer is designed to do three things: to convert neutral atoms or molecules into a beam of positive or negative ions, to separate the ions based on their mass to charge ratio, and to measure the relative abundance of each type of ion. From this information, we can determine both molecular weight and molecular formula, as well as gain some structural clues. Samples of gases and volatile liquids are introduced directly into the ionization chamber. Mass specs are kept at a high vacuum, which vaporizes liquids and some solids. We can actually link mass spec to something like liquid chromatography or gas chromatography, which gives us a lot more information than just an MS alone. In the ionization chamber, molecules are bombarded with a stream of high energy electrons. Collisions between the sample and high energy electrons result in the loss of an electron to form positive ions. The molecular ion, or M+, is the species that is formed by the loss of a single electron from a molecule. So let's take methane, for example. When methane gains an electron, we form, we're going to lose an electron in this process. I'm sorry, I can't read my own notes here. And it really doesn't matter which electron we lose, which is why we write it typically like this, where we have a positive charge and a radical. These belong to the unique category of ions known as the radical cation. And for us, which electron is lost depends on the ionization potential. And to us, it does not matter which electron is lost, which is why we write it like this. Any of those electrons can be lost, and it still ends up as the radical cation. A molecular ion, like the one seen here, can undergo fragmentation to form a variety of smaller cations. This is the molecular ion that you saw on the last slide. The ion beam focuses these ions into the mass analyzer, which is at the end of our spectrophotometer. And this results in, I guess I don't have a picture of it, in a mass spectrum. So mass spectrum is mass per charge ratio on the x-axis and intensity on the y-axis. You'll see in mass spec some amount of lines. The highest line is called the base peak. The base peak is arbitrarily set at 100 intensity, and everything else is recorded as some amount of that base peak. The number of peaks recorded depends on the sensitivity of the detector. There are several types of mass spec, and they all do the same thing with some variation. These include electron ionization mass spectrometry, matrix-assisted laser desorption ionization mass spectrometry, and several others. Resolution is how precisely you can measure the mass. A low-resolution mass spectrometer is capable of distinguishing ions with nominal mass, so they differ by 1 or more atomic mass units. So this one could distinguish, for example, between 24 and 25 molecular weight. High-resolution mass spectrometry can be much more precise, so it can distinguish between 54 and 54.0001 atomic mass units. Isotopes are common in both nature and in mass spectrometry. You learned about the M+ peak just a second ago. That's the molecular ion peak. We can have an M+1 peak or an M+2 peak. An M+1 peak is the presence of one heavier isotope. So something like carbon-13 or nitrogen-15. The M+2 peak is going to have two heavier isotopes. And mixtures of isotopes are very common. You can see in this chart the relative abundance of these isotopes. So let's go ahead and look at some examples of mass spectra. So this is chloroethane, and chlorine is 75% 35Cl and 24% 37Cl, which means we will have an M+2 peak here. You can actually use the isotope abundance to calculate how many chlorines are present in this molecule. That's beyond the scope of what we're going to do in this class. Your base peak or your M+ peak is 64 here. And that one, in the case of chloroethane, gives you your molecular weight. Now you can see that there is also a 29 peak here that's pretty high. The easiest thing to do with mass spec is to look at your base peak, and that's your most abundant ion. It is not always your M+ peak, and you'll see that here in just a little bit. This 29 is likely due to a carbon, which is 12, 3 hydrogens, which is 15, another 12, 27, and then 2 hydrogens, 29. We typically write this as 29 being that CH2CH3 fragment and the chlorine being kicked off. Bromopropane is similar. So we've got an M+2 peak at 124, our M+ peak at 122, and that's our molecular weight of our molecule. Our base peak here is at 43, which corresponds to CH3, CH2, CH2, with a loss of that bromine. If there's no M+2 peak present, then oxygen, sulfur, chlorine, and bromine are not a part of your molecule. These are the only elements that give significant M+2 peaks. The other thing that's very helpful when looking at mass spec is the nitrogen rule. The nitrogen rule says that an even number of nitrogen atoms means that you will have an even M+ peak or an even M/Z. An odd number of nitrogen atoms, so one nitrogen atom, will give you an odd M/Z value. This is the molecular spectrum, mass spectrum for octane. And again, you see the fragment for 29 is CH2CH3. The fragment for 43, which is our base peak in this case, is a 3-carbon chain all the way up to a 6-carbon chain. Again, we see our M+ peak all the way out at 114, indicating that the molecular weight of this product, of this molecule, is 114. Here's 2,2-trimethylpentane. So let's draw that out. So pentane 1, 2, 3, 4, 5, and 2,2-dimethyl. So the first thing I would look for in this molecule, in this mass spectrum, is this peak. I would look for something that has 4 carbons, 3, 6, 9 hydrogens, and that indeed is our base peak at 57. Methylcyclopentane, you can see that this gets cut in several different ways with a base peak at 56 and an M+ peak at 84. Butene is going to get split at a molecular ion of 56 and a base peak of 41. That base peak is the loss of a methyl group. Alkynes show a strong molecular ion peak. So for, let's see, pent1-ine, we have a molecular ion peak at 67. I'm sorry, a base peak at 67 and a molecular ion peak at 68. This undergoes some rearrangement to give us this major peak at 39, as you can see in the propyl cation at the top of this screen. Butanol similarly undergoes some rearrangement. You can see a double bonded structure at 28 and a double bonded structure at 31. Alcohols are rather complicated in terms of their mass spectra, but it does provide us some useful information. Octanone, you can see here a molecular weight of 128 and a base peak of 43. Butanoic acid, this is where it starts to get a little bit more complicated. The M+ peak is not usually present in carboxylic acids. We have a big base peak at 60. And at 45, we have the C double bond OOH side of the molecules. So that's this part here would be my peak at 45. My peak at 60 is a result of McLafferty rearrangement, which looks like this. McLafferty rearrangement occurs in molecules that have long enough chains to do this rearrangement process right here. So the oxygen in both cases here goes and gets the hydrogen from a carbon that is 3 carbons away. That results in a double bond that gets moved all the way over to near where the oxygen is, and that breaks apart right here so that we get 2 different products, and this would be the base peak, or at least a large peak with McLafferty rearrangement. Methylbutanoate is an ester. We get a base peak of 43, a molecular ion peak that is largely absent at 102, and alpha cleavage and McLafferty rearrangement are both very common. So alpha cleavage is going to be at 71 and 59. So let's see if we can figure out what those are going to look like. So 1 carbon, 2 carbons, 3 carbons. That would be 12, 24, 36, 37, 38, 39, 40, 41, 42, 43. So that's our base peak. Oops, missing an O. So our base peak is this way. If we add a carbon double bonded oxygen to that, we would get 55 plus another 16, which would be 71 if I did my math correctly. So that's the 71 of our alpha cleavage. And then our OCH3 is cut off there. Aromatic hydrocarbons undergo a fragment rearrangement that results in a tropylium cation. Something that has benzene in it is always going to show a strong molecular peak at M/Z of 91. Amines undergo a characteristic fragmentation pattern, as you can see here. It's called beta cleavage. So alpha cleavage right next to our functional group, beta cleavage 1 carbon away. This shows a base peak at 30 and a relatively insignificant peak for our molecular ion at 87. Mass spectrometry is very useful to us. It is probably the least useful thing that you will do in terms of IR, NMR, and mass spec, but it's actually very, very useful to us in things like forensic science, as well as luggage screening and routine molecular identification, both in protein sequencing as well as simple organic molecules. In class, what I will give you are several mass specs, and I will ask you to identify the molecular ion peak as well as the base peak and the ions responsible for those based on a known structure or structures that you will have to identify the mass spec from. I will not ask you to identify the molecular weight or the molecular formula based on mass spec. That's outside the scope of what we're going to do in this class. I hope you have seen that mass spec, IR, and NMR are all very useful analytical tools, and I hope you will use them as such to help you identify structures both in your worksheets, your exam, and as you move forward in organic chemistry.